So, hello everyone, welcome back to this GFG POTD streak of day 153. And if you are new to this channel, please like, share, and subscribe so that you can learn, maintain, and grow our streak together. So, let us see what today's question is about. The question name is BST, maximum difference, and the tags given here is our DFS and binary search tree. So, let us see what the question says, and then we will proceed ahead with the coding section, right? So, I've already done this problem. Let me reset my code editor, and we will proceed ahead. Okay. Okay, so the BST maximum difference. So what if you have read this question, it is very easy to understand first of all, and it is a very standard question as well. So let us see. You are given a binary search tree and a target value. You must find the maximum difference between the sum of node data from root to target and from target to a child leaf node. Initially, you are at the root node, right? And if the target node is not present, then you have to return -1. So for the first example, what they have said that your target is 20, right? So in a BST, you can clearly search in a tree, right? Because there is a property of BST that the right child should be greater than the root and the left should be lesser than the root. So to searching a node, it's very similar. You can do it in iterative form. You do not need a recursive thing in that, right? Because you already know in which direction you have to proceed depending on the value of the node. So in the iterative code, we can just directly reach to this 20, right? And when we are reaching to this 20, we will maintain the sum from the root node to this target node, right? But after this target node, so let us, after this target node, you have to find the path sum. So after 20 is just one node, it is 15 and 22, which is leading to the leaf node, right? So either you can do till 20, the sum was 25, and now from 20 target to leaf you will get a sum of 15. So 25 minus 15 will give you 10. Similarly, the other way would be 25 minus 22 will give you 3, right? But you need to find the maximum answer, right? So it would be 25 minus 15, it's 10. So the first thing that we need to do is the step one would be to wait a second. So the step one would be that you just need to hmm, so switch back to the paint section again because it's a very light software. There's no lag here, right? So the first step would be the search the target node in the BST, and the searching is very easy, right? So this is, let's say, 25, right? And you have to search 20. So the target node to be searched, if less than the root value, then definitely you have to go in the left direction because the left value is always lesser than the root node. And so let's say the target node was 30, then definitely it is greater than our current root value and you need to search for the greater values, right? So definitely will go in the right hand section, and you can clearly decide at such point that either you have to go left or either you have to go right. So that will be the time complexity to search a node in the BST would be nothing but the height of the tree, right? Height of the tree. So definitely we can code this step, and once while we are traversing to search the node, right? So if I just write the pseudo code, so let's say uh, if current dot data, right, is less than target. If target is greater, then you have to like move right, right? And if not, then in the else case, then you have to move left. But while doing these things, you have to make a, let's say, sum variable as well, and you will always maintain a sum of the path that you are taking to find the target node. So here one additional step will be that sum is equals to sum plus root dot data, right? I hope we are clear to this point. Okay. Okay, so let us code this thing first and then we'll proceed ahead, or let us discuss. So now we have reached to our this node. So this is 25, this is 20, and this is 22, and this is 15, right? So assuming that I'm drawing more trees here, so let's say after 15, let us assume that this was not 15, this was 19, just for the case of explanation of the different cases. So 19, and let's say this is 18, right? And now let's say for 12, the right left child is 1. So now you are here at this point, right, which is storing in the current node, let's say, right? And you have a sum which is pointing to 25. Now from here you have to consider each and every path, right? So each and every path. So to form a path, either you can go to left or either you can go to right, right? So when you go to left, they would have another child also, let's say x here, and you have to consider this path also from 20 to 19 to x, right? Because this would be the leaf child and you not proceed ahead. Other path would be the 20 to 19 to 18. The other path could have been 20 to 22 to 1, right? This would, so you have to consider for each and every left, you have to consider each and every right as well, right? So definitely you have to use recursion here. Since this was the BST, then we know that in which direction I have to move. That's what I have. The search code could have been done in the iterative form. So in case that if would have been it would have been the binary tree, then again you have to do the recursive code to search the node also, right? So we have a use case of for each and every right we are taking, we have to go left also to consider each and every path, right? Okay, so let us do the first step, right? And this will be our second step. This will be our step two to code the recursive approach. So I have given you the pseudocode for the first step. Let us code that thing, and then we will proceed ahead. Great. So what can we make? That let's make a some variable that is pointing to 0, right? And then let's start the search thing of in BST. So I'm pointing the node current as my root node, and then I will run a for loop that while current is not equals to null, right? I will move in the right direction, the left direction according to my target values, and I will stop when I reach the target. So let me code that thing and I will come back to you, and meanwhile you also try to code it yourself. Okay, I guess I have paused my video somewhere around. So let me explain it again. So how the code has been written is that if it is equals to target, we need to break it, and if we have to break out from the loop of the traversal of search, and if the target is greater than the current node, right, then definitely we have to move in such a direction where the greater node is present, and the greater node is present in the right direction, and else in the left direction. Now you can read this note point here that if the target is not found, then you have to return -1. So suppose the target was not present in the T, then my current will be pointing to which value? It will be pointing to null, right? That it has traversed all the tree, but it has still not found the value. So in that case, I just have to return -1, -1, right? Yes, that is it. Now the cases would be, now there will be a else case that the target is found and you have, and now you need to uh, uh, find all the paths that is possible from that node, right? So let's say that your target is found, right? And but that target is your leaf node, right? So that would be that it's, how can you make sure that the current dot left would be equals to null, as well as its right part would also be equals to null, right? So that makes sure that you have found the target, but the target node itself is a leaf node. So in that case, there would be no available path, right? That you have to difference from the path that you have taken from the current node to the target value. So in that case, you will just return the sum, right? Now in this else, you will have some other things that now let me write a comment and then we'll explain. Hmm. So from here on now, we know that we have a target node and the left and right subtree exist, right? So we have to consider all the path, that is while traversing the path, we have to maintain the path sum as well. And if reach the leaf nodes, then we have to return the maximum difference. So let us write a function, right, so that we can move left and right. So to move left, we have to check that if current dot left is not equals to null, and similarly we have to check that current dot right is not equals to null, and then we will call a recursive function. Why recursive? Because for each and every right we will make from that node, have to consider the left part also, right? So that could be done via recursion itself, just as you do a search in a binary tree, right? So let us name the function as solve, and in that thing we will pass some parameters, that is we are searching from the node that is current dot left, right? And then we are passing the sum value because this will be needed to uh, to uh, maintain our difference, right? and then this is my current path value, right? The path I'm taking, I'll be incrementing in this. So as I'm starting, so it would be 0. Similarly, I will do for the right thing as well, right? Okay, so it would be current dot right. So now let us understand how that recursive function we have to write. So we will make a recursive function here, right? So what we would do that, let's make a function, name it as solve, and there will be some certain parameters. That is, we will start from let's say node, which will be pointing as root, and then you have a path sum. That is the path you are taking. You are considering the sum, and then you have the sum value. This sum is nothing but the sum of the path you have taken from the root node to your target node, right? And then you have to maintain the maximum difference of sum minus path sum, right? So the base case would be that whenever while traversing, we have to reach the leaf node. So if we have reached the leaf node, then we have to stop, right? So we will just write a base case here that if root dot left is equals to null. Similarly, for the leaf node, the root dot right would also be equals to null. So let me write that part first. If it is null, then what we have to do, let's make a static variable, let's say result, right? And initialize it with minus infinity, because we have to compare with the maximum value, right? So what I will write, that result will be is nothing but the max of result comma sum minus, since this we have reached our leaf node, and you have to consider that also in your path sum, right? So what I will do, that sum minus the path sum, right, and plus the root dot data. So that will give you the track of your maximum difference, right? This it will be over here. So now what you can see is, now let me show you a dry run, that from this 20, right, this was your current value, and I started traversing from here, right? So first I will call, my left is not null, so I called for left, and my path sum, I'm writing it with PS, so it is now 19. This 19 will again call the its left part, right, because it is not null, right? So it will call for 19 plus 18, and then this 18 has been reached to the leaf node, so it will consider the leaf itself, right? And now your result will be stored as 25 minus 19 plus 18. So whatever you will get here, what you will get, 37, right? So 25 minus 37, it will be, let's say 7 plus 5, 12, so it will be minus 12, right? But that's not the thing. The numeric integers are not our here main goal. We have to see how the traversal is happening, right? Similarly, it will then return to its previous call, and it will see that the 19 has a right child or not. So it do not had, right? So that means, but still it will call for root dot right. So that means we have to handle one case as well, that if root is equals to null, then you need to return from there, right? And there are two functions call. We will make a two functions call. We will dot solve. You go for left. For each and every left, you have to make a left, right? And in the path sum, so I'm writing this variable as PS, you have to do root dot data, right? And this, and pass this sum variable as well. Similarly, for the each and every left, you have to make a right? So it will go root dot right, comma PS plus root dot data, consider that data into the path sum, and then pass the sum variable. So that will be our entire code, right? So it will compare with 19 has no 19 will call for the right shell, but it will not form. It will say it will fall into this condition if it is now return. So it will now return against to its parent call, that is 20. So now the left call is completely over for this thing, and it will go for 22, right? It will go for right, and it will go for right, and the first call is for left, so it will go to 1 again, right? Similarly, now for this thing, the PS will be updated as 22 plus 1, and since the 1 is the leaf child, so in this case my result will be updated as 25 minus 23, that is 2, right? So now previously it was minus 12, now it is 2, so it will be, the answer will be updated as 2 via this statement, right? Now 1 will again go back to its parent call, right, 22, and it will see that 22 do not have any right child. It will fall into this case, that's why it's going to its right, and it will see it do not have a right child, then the root is equals to null. It will this condition will occur, and it will return, and it will get back to 20. Now the whole traversal is complete, and it has returned to its original value where it started, and the traversal will be over, right? So I hope you were able to get a clear picture. So I highly recommend you to pause this video now, and maybe try to run one or more test case using this pseudo code, and try to try to code this pseudocode in your editor, right? And then we'll proceed ahead. So I mentioned the same exact pseudocode which I explained you, right? So we handle the two cases, that if current equals to null, we have to return -1, and if the node itself is our, what, the the leaf, then you have to return the sum, right? Just the above part, that is from the sum of the node from the root data to the target node, because there is no another path left from the target node to leaf, because the target node itself is a leaf. And if that's not the case, then you have to consider each and every path starting from its left child of the target node and from the right child of the target node, and that is why we needed recursion, right? And we are storing, uh, we are doing everything into a result, right? And since we have accessed this result variable, we have to make it first of all as result is equals to integer dot min value, right? And since this is accessed in the recursive and we are not sending it as a parameter, right? So that means we have to make it as a global scope as well. So we will write it as static int result, right? Yeah, we have to just declare out of the function so that it will be accessed by each and every function, and we have to initialize inside the function, right? We have initialized it here at line number 89, and then everything is taken care of. So this was the tree question, and I always say that whenever there is a tree question, try to dry run for a small tree, because whenever a tree comes, it is all about recursion and how you traverse to get your answer, right? And that is the reason I have started my DSA playlist with the recursion topic. I have completed that topic. You can go and get an idea how the recursion works, and my next topic I'm starting will be of tree. So yes, stay tuned and everything will get aligned in the order. So let us compile and run, and we'll see that the traversal we have made, it is correct or not. So let us wait. So we have this return statement. Okay, so we have not returned it, right? So here we have to write that return result. Yes. Let us compile and run again. So definitely the test cases passes. So this -1, oh, that means the target node that is to be found here is present, but it's 2, right? So that means the difference is coming as negative. Yeah, that's the case. So the expected and our output matches, and I let us read the question again, that what's the constraint and any other things that we have not taken care of. So yeah, there is no other test cases. So the expected time density is O of n, and auxiliary space is height of the tree. So definitely this while loop is taking your height of the tree, right? But this recursive solution will be, in the worst case, it will be taking O of n, because let's say the target node was the root itself, right? So in that case, to consider all the paths sum, you have to go visit each and every node. That will give you the time compressive O of n. Similarly, the recursive stack space will be height of the tree. As you can see here from this recursion pattern I showed you, for this 20, I went to 90 and then went to 18, and 18 calls back to its parents, right? So this callback is stored in an internal stack for the recursion, right? So in the worst case, this stack will have the space complexity, that is, it will be storing all the uh, no, all the nodes of the tree which is in a height order, right? Let's say the skew tree, 19, 18, and now, right? So it would be height of the tree. That's the basic understanding. Every tree have the space complexity of height of the tree. Yeah. So that is it. So let us hit the submit button, since the constraint is 10 power 4 and we have put it in O of n. So it will definitely get submitted. So let us verify that as well, and we will end this video. Okay, so one mistake I have made here is that I have passed the function as path sum as my second parameter, and so the path sum would be 0, right? And the sum I have passed in the third parameter. So let me rechange that. It would be sum 0 comma sum, right? So that is it. Let us hit the submit button again and we will verify it. So great. I think all the test cases will be passed. Let us wait for the 5 more test cases. Yeah, definitely it has run, right? That is it. That is it for the today's video, and the code I needed to show you for the C++ as well. So in the right hand side, we have the Java code I explained to you line by line, and in the right hand side, in the left hand side, you have the C++ code. The same thing I have written, it's written in C++. Just the dot thing has been accessed by this arrow mark and each and everything. Let me scroll it for you so that you can have a more clearer understanding, right? And the same code I have tested on the editor also, so it successfully ran, right? So no need to run the C++ code again. So that is it for today's video. Let us meet in the tomorrow's video of day 154, I guess. Yeah. Till then, keep learning, keep growing. Bye bye, and take care.